Hello, awesome Algebra 1 students, and welcome to your second lesson in Topic 5. As a reminder, our theme for Topic 5 are piecewise functions and linear absolute value. Really, these first two classes are kind of all about piecewise functions, and we'll define what a piecewise function is soon. And then 5.3 next class is going to start to make the jump between a piecewise function and an absolute value function, and then we'll finish off Topic 5 all about absolute value functions. So, let's begin. Your opener is a reminder from last class. They're going to have you graph two linear equations with restricted domains. So don't forget, you're going to graph one of them, and then you're going to graph the other one. Don't forget, after, you should probably do this in pencil because you are going to want to start to erase part of that graph. Good luck. I'm excited to see your success. Unpause when you're ready. Alrighty. There are a couple ways to do this problem. Now, one thing you could do is you could start with the point where you're going to erase. And you could do that by taking this value, this one value, and substituting it into your equation. And I'll show you an advantage of doing that. So remember, when you substitute 1 into this equation, you find f of 1, which is 1/3 times 1 plus 2 minus 2. Okay, you can do all this on your calculator if you'd want. 1/3 of 3 is 1. 1 minus 2 is -1. So what this built for us is it built us an input of 1 and an output of -1. 1 comma -1. However, we also know that there is no equal sign here, so this point has to start with an open circle. Once you're there, how do you build the rest of the line? Well, you use the slope. And the slope tells us to go up 1 over 3. Up 1 over 3. And although that works, don't forget that we only want x's that are less than 1. So if we have our wonderful wall here, this is x equals 1, we should remember that any x's to the right of 1 are x's that are larger than 1, and any x to the left of 1 are any x's that are less than 1. And so, because we only want x's that are less than 1, I actually want to reverse that slope and go down 1 to the left 3, down 1 to the left 3. To finish this off then, we're going to go through and connect just up to that point, and now we have our graph with the restricted domain. It's always important to see a couple different ways to do this to decide what you think is going to be fastest, because you could have done this our normal way too. And the normal way is to start at the point opposite of h comma k, -2, -2, that's here, and then gone up 1 over 3, up 1 over 3, down 1 over 3, and connected all of these together. Then you go back through and decide where to erase, and so you erase the part that's on the right side, and then you have to go back through and do the open circle. So the advantage to doing it the way that I did in yellow is it tells you the point that's at the wall at the stopping place, and then you just have to use the slope to move to the correct side of the stopping place. There's no erasing if you do it this way. So I'll give you one more example. This one is only going to be a piecewise function for x's that are greater than or equal to 1. So to do that, I'm going to find g of 1 again, because there's a 1 right here. And that gives us -1 plus 3. That's the same as 3 minus 1, which is 2. So that gives us the point an input of 1 and output of 2. 1 comma 2. There's an equal sign, so that's going to be solid. And then we use our slope, down 1 over 1. Which way do I go? Well, again, if you remember that this wall is right here at 1, the values to the right of 1 are for the x's greater than 1, and I think that's what we want in this case. We want x's greater than 1 on our graph. So I'm going to go down 1 over 1, like so. We know that that point in the middle is the stopping point. That's our invisible wall, and so I'm just going to go here. And so that's a nice way to graph a linear function with a restricted domain without having to erase anything. Okay, let's jump on to our lesson for today. A piecewise function is created by putting pieces of multiple equations, usually functions, together in one single equation. It's somewhat like what we did with systems of equations and systems of inequalities. Remember, with systems of equations, we took two equations that were separate, and then we put them onto the same graph. Well, it's a similar idea here, but we're not trying to solve. Because usually, if you put all the pieces of a piecewise function together, they just make one function. So you would see something that looks like this. H of x equals this. We have this line, but only a piece of it, and then this line, but only a piece of it. When we graph, there are just a couple steps, right? Our first step is we need to graph y equals negative x plus 3 for x greater than or equal to 1. Then, luckily, we've already set the stage and done that for us. This starts at the point 1 comma 2 and goes down 1 over 1. I'm going to leave off that invisible wall for now. I don't think we need it. The second step is we need to graph our other equation, which was 1/3 times x plus 2 minus 2 for x less than 1. Okay? We saw that this one started at 1, negative 1, open circle, and we go down 1 to the right, 1, 2, 3. Down 1 to the right, 1, 2, 3. And I think this, if I were able to draw a better line, is our full piecewise function. Now notice that this is still a function, right? We've said before that a function always passes that vertical line test. It only has one input for each output. So we have this vertical line test going through. But you might say, whoa, look at that vertical line. That passes through 2 points. But don't forget that it doesn't pass through 2 points, because this open circle means that there is no point there. That open circle means follow this graph and then stop right before you get to an x of 1. There's no actual point there. The only point at 1 is this point up here. And then we can go back through. So this is still a piecewise function. You'll know if you did this correctly if you don't have two lines sitting on top of each other, right? For example, let's say that you did this green graph, but you went the wrong way. You went up 1 over 1 because you didn't realize which way you were supposed to be keeping it. Well, I would almost automatically know that this is wrong, because is this a function? No, the vertical line is passing through multiple points at the same time. So if you do this piecewise function section correctly, you should have, if I could redo this, there we go, you should have your functions on either side of the wall. One to the left side, one to the right side. There's really nothing else to this, so let's go ahead and get some practice in. There are 4 practice problems on this page. You're going to want to graph each equation, and you can do it either way. You can graph the full equation and erase, or you can graph the starting point and use the slope from there. Once you've done that, then you have a couple questions to answer at the bottom. Good luck, and once you're done, come back to us, and we'll see how you did. All right, so looking at these, we have to graph each function, then evaluate the function at the given values, and then we're going to draw an arrow from our point to the corresponding point on the graph. So let's do it a bit at a time. I'm going to start with the 2 functions up above, negative 1x plus 1, and this one's going to be 1x plus 0. Do that in a different color though, so it stands out. First thing I like to do is start with the wall. So 0, let's see, this is when x is negative 3, negative 2, negative 1. Oh, I think when x is 0 has to be at the origin. Well, if it was x is negative 2, it would look like this. So when x is the origin, it looks like this. Now we have 2 equations here. I'm going to do one in red, one in green, and we'll know if we've done it right if one equation ends up on one side of that wall and one equation ends up on the other. I'm also going to do it with that other method I showed you to start for today. So I'm going to start with 0, substitute it in over here. So if we substitute in 0, let's see, what is that going to be? It's negative 1 times 0 plus 1. Okay, so this is when x is 0. That's 0 plus 1, which is 1, so it gives us the point 0, comma 1. Notice that there is no equals sign on this, so there's an open circle. Okay? And then we need to go down 1 over 1. So down 1 over 1. Now which way? Well, we only want x's that are less than 0. And hopefully at this point we're getting pretty comfortable knowing that to the left is less than and to the right is greater than. So although I could go down to the right here, really I'm actually going to want to go up one to the left one to see the first part of my piecewise function. And then our second one is 1x plus 0, so I'm going to again take the 0 right here, and that I think just gets us 0. That tells us when we input 0, we get an output of 0, and so I'm going to start at 0, 0. We want to use a closed circle here because there is an equal sign, and then we are going greater than 0 to the right, so up 1 to the right 1, and we end up with our function like so. This is still a function. It passes the vertical line test. So let's go ahead and work these three problems down below. F of negative 1, f of 0, and f of 1. Well, this is actually a really important ability for piecewise functions, because with a piecewise function there are, and I'm going to try to clean this up a little bit, there are two what I call branches to this piecewise function. There's this top branch that I graphed in red that we only use for x's less than 0, and there's this bottom branch that I graphed in green, which we only use for x's greater than or equal to 0. However, this whole function is called f of x. So let's go ahead and try to use f of x and figure out which branch we need to do. They first ask us to substitute negative 1 into f of x. In order to do that, we need to substitute negative 1 into one of these x's. Which one? Well, we have to think, is negative 1 less than 0 or greater than 0? And I think in this case, in any case, negative 1 is less than 0. So that tells me I need to use the equation in red, and instead of negative x plus 1, we need to replace the x with negative 1. So to find f of negative 1, we use this top part, and we substitute negative 1 into the top branch. Then we go through and we work this out. This is something you can do on your calculator or by hand. 1 plus 1 just gives us 2. That tells us then that we built the point. The input is negative 1. The output is 2. Last but not least, they ask us to draw a line from this point to our graph. Well, is negative 1 comma 2 on our graph? And yes, it is. And notice that it's on the red piece of the piecewise function. Okay, let's try the next one. F of 0. Okay, f of 0 is asking us to take 0 and substitute it in for the x that's up here. However, we're only going to use one of these two equations. Which one? Well, this top equation in red is only good for x's that are less than 0. I don't think 0 is less than 0. However, the bottom equation is good for x's that are greater than 0, 0 is not that, or equal to 0. So this has got to be the branch of the equation we're going to use. We're going to use this guy. So to find f of 0, it just says take x and replace it with 0. There's no other math to do. That's pretty easy. So when you substitute in 0, you get 0 as an answer. And so can we see that 0, 0 is on our graph? That's a nice way to check to make sure we're doing everything correctly. Let's try our last one. The last one asks us to evaluate f of 1. Which branch is good for f of 1? Well, 1's not smaller than 0, so that one's out. 1 is greater than 0, so we're using the bottom branch. f of 1, replace the x with the input. That's 1, and there's no other math to do. This is the point 1 comma 1. And notice that that is also on our graph. Okay, if you didn't understand this when we did goal 10, which was function notation, notice that this or these 3 points right here show up on the graph up above. F of negative 1 is 2, f of 0 is 0, and f of 1 is 1. Hopefully that gives you enough guidance for the others, but I am still going to keep talking you through it. You should probably pause me and do it on your own. I hope you can do it faster. Alright, so wall first, that happens right at 1. This is when x equals 1. Anything over here are the x's that are less than 1. Over here are the x's that are greater than 1. Then we start to graph. Well, right at the wall, we can have a closed circle because there's an equals, and we just have the output being equal to 2. If the output equals 2 when x is 1, then that is like the point 1 comma 2. Technically, this just means y equals 2, and we've seen that before. Y equals 2 would normally just be a horizontal line. However, I'm not going to do the whole line. I'm just going to do the part of the line that has x is less than 1, which means this line needs to start at the wall and go to the left. All right, let's go ahead and do that second equation. This one's in HK form, so although you could start at the point 3 comma 1, there's nothing wrong with that. I guess I should color coordinate this too. I'm going to try the other method where I'm going to substitute 1 in first. So 2 times 1 minus 3 plus 1. And just through a little mental math, that's negative 4 plus 1, that's negative 3. So 1 gave us the point negative 3. That shows me right what happens at the wall here. We can't be equal at 1, so we need an open circle at the point 1, negative 3. From here, we use our slope up 2 over 1. You could either go up 2 over 1 to the right or down 2 to the left, 1 to the left. But because it's greater than 1, we only want to go to the right. And then we connect. There we go. Piecewise function, nothing too bad. Then we need to practice using our piecewise function, so they want us to find h of 0. We need to ask ourselves, is 0 greater than 1? No, so we're not using that equation. Is 0 less than 1? Yeah, so we just use the top equation. This top equation says when you do h of any number, the answer is always 2. So that's easy. H of 0 is 2. And notice the point 0, comma 2 is this guy right here. It is on our line. What about h of 1? Well, h of 1 means x is equal to 1, right? These are our inputs, our x's. X is equal to 1, and so we still want to use this top equation. When we input 1, the answer for the top branch is always 2, so we need to make sure 1 comma 2 is on our equation, and it is. Last but not least, h of 2, well, 2 is greater than 1, so I need to use the other equation. And that says do 2 times whatever x is minus 3 plus 1. X in this case is 2. Through a bit of math, negative 1 times 2 is negative 2. Negative 2 plus 1 is negative 1. So this tells us when we input 2, we get negative 1 as an answer. And we know that we did it correctly because 2 comma negative 1 is on our line. Okay, 2 to go. Oh, this one's interesting. This one has all the same number over here for our domain restriction. So I'm going to put that wall at negative 2. This is x equal to negative 2. These numbers over here are all the x's less than negative 2. And these are all the x's that are greater than negative 2. Let's go a bit at a time. The first thing I'm going to do is I'll do the top equation in red, 1/2 x. And it says we use this when x is equal to negative 2. So let's see what happens if we substitute in negative 2. Half of negative 2 is negative 1. So when I substituted in negative 2, I got negative 1. X is equal here, so we put a point. And then, which way do we go? Well, this slope says to go up 1 over 2, up 1 over 2. But which side do I go to? Well, we only want to use this red equation when x is equal to negative 2, and that only happens right at that invisible wall. So actually, this top equation, when it's just equal, is just a single point, and so I'm done. Let's look at the next. Normally, you would treat this as 2x plus 0, but if we use our other method, I'm just going to take this negative 2 and substitute it in. 2 times negative 2 is negative 4. So that gives me the point negative 2, negative 4, which is down here. We can't be equal to negative 2, so that's got to be an open circle. And then we only use this branch of the equation for x is greater than negative 2. Greater than negative 2 is on the right. So my slope, 2 over 1, says to go up 2 over 1, and it looks something like this. Last but not least, we have negative x. We'll do this one in blue. Okay. To substitute in at negative 2, negative 2 is positive 2. So that makes the input negative 2, that's on the wall, and the output positive 2. We can't be equal there, so we put an open circle at negative 2 comma 2. Then we only want to use the part of the graph that has x is less than negative 2. Less than is to the left. And a negative slope means we're going down. So following that negative 1 that's hiding here, going backwards, shows us that we just have this part of the line. Notice this still passes the vertical line test. If you were to take a vertical line and drop it anywhere, it only touches one function. Even right at that wall, there are no points here. That's why there are open circles, so it only touches one point, the red one. Let's try a little substitution here. To find f of negative 3, which branch will we use? Well, negative 3 is over here. That's on the less than side. Less than negative 2 is going to be the negative x, so we do negative of whatever x is, and it looks like x is negative 3 here. Negative negative 3 is positive 3. So this tells me that when we substituted in negative 3, we got an answer of positive 3. And fingers crossed that's on our graph, but I think it is. Negative 3, comma 3 is perfectly right there. F of negative 2, so x is equal to negative 2, that's our top branch. And we already substituted that in. We saw that's negative 1. Negative 2, negative 1 is also on our graph. Last but not least, we had to find f of negative 1. Negative 1 is, let's see, larger than negative 2, so we use the 2x1. We're substituting in negative 1. 2 times negative 1 is negative 2. Negative 1 comma negative 2 is right here. Good. Looks like everything's matching up. Last one. 3 functions again, and it looks like this time we have 2 different domain restrictions. Tricky, tricky. Okay? One of them is going to be at negative 3, so let's go ahead and put this one. That's when x is negative 3. Okay? And the other is when x is 0. So that's right through the x-axis right here, and that's when x is 0. All right, so now we've divided our graph into 3 sections. Everything that's over here are the x's greater than 0. Everything to the left of negative 3 are x's less than negative 3. How do we describe the section between negative 3 and 0? Well, they've actually already done that for us up above. That's going to be our negative 3 is less than x, which is less than 0. Sorry, it's getting a little sloppy over there. We'll do this. There we go. All right, 3 sections probably means 3 pieces of lines, piecewise function. Let's start with our top one. I'll do this one in yellow, x plus 3. Now I know that that's less than negative 3, but it's going to have something to do with this wall. There's no equal, so open circle. When we substitute negative 3 in for x over here, negative 3 plus 3 is 0. So the x was negative 3, the output was 0. Negative 3 comma 0 is right here. It's on the x-axis. Open circle because there's no equals. Then we use our slope that's hiding out front, and we could go up 1 over 1 to the right, but it tells us we only want to use this equation for x's that are less than negative 3. So I'm going to follow this backwards, and this is the only part of my line we keep. Next up, we have the output is 4 for any x's between negative 3 and 0. Y equals 4 is normally just a line straight across. However, we only want to keep that horizontal line between negative 3 and 0, between the 2 walls. So I'm going to go ahead and do this, and then think about the endpoints. X can be equal to negative 3, close circle. X is not equal to 0, open circle. And then we move on. Last one we'll do in blue, 2x plus 1 only works for x is greater than or equal to 0. That's this region. We start by substituting in 0 to see what happens at that divider. 2 times 0 plus 1 is 1. So when I inputted 0, the output was 1. 0 comma 1 is here. And this is a closed circle because of the equals. Then we use our slope. Up 2 over 1, up 2 over 1, and we have the final piece of our piecewise function. Whew. All right, let's finish this off. G of negative 4. Well, which branch up here would negative 4 use? Negative 4 I think is smaller than negative 3. I think we have to use the top branch. So this is going to be negative 4 plus 3. That's the equation, which is negative 1. So when you substitute in negative 4, you end up with negative 1. And you'll notice that that is on the graph. Okay, next we have to evaluate g of negative 2. So if we look up here, negative 2 is not smaller than negative 3. Negative 2 is not greater than 0. Negative 2, I think, is in between negative 3 and 0. So to evaluate g of negative 2, we have to use the middle branch, which is easy because it tells us regardless of the input, the output is always 4. Negative 2 comma 4, hopefully that's on our graph, but it is negative 2, oops, and that's where we realized that I made a mistake. I said that it was 4 and I drew it at 3. Awkward. There we go. It's a good thing I was checking that. See? Easy to make mistakes. Second try is the charm. Negative 2 comma 4 is on our graph. It's the point right here on the line. Whew. All right, 1 to go. G of 2. Well, let's see. G of 2 means 2 is the input. Just looking at the graph, I think that means we're using the blue equation. And yeah, 2 is greater than 0. So we do 2 times whatever our x is plus 1. And that's 4 plus 1, which is 5. So 2 comma 5. Let's see if I did this graph correctly. 2 comma 5. Yeah, that's right up there. That's looking pretty darn good. Okay, well, now we're just going to work backwards, and it shouldn't surprise you too much. We want to be able to go ahead and graph functions, but we also want to be able to write an equation from a graphed function. The first thing we're going to do is we're going to look at these piecewise functions, and we're going to see if, without writing the equation, can we determine the outputs when we're given an input. This is tying everything back to function notation. We need to make sure we're comfortable with that. It sticks around for a long time in mathematics. In function notation, we need to remember that the value substituted into our equation, and this is g of x, I should probably say g here, whoops, this is g of x. X is our input. So all of these numbers here are inputs. They are the points negative 2, 0, and 1, all comma something. How do we find the something? Well, g of negative 2, we just go to the x-axis. Here's my x-axis. We go to negative 2, and we think, is there a point on one of these lines that has an x value of negative 2? Well, yeah, I think so. I think this is the point negative 2 comma 0. And so that tells us if we had an equation and we substituted in negative 2, the output should be 0. If I wanted to evaluate g of 0, we go to the x-axis to 0, and we say, is there some point here where it is on the graph? Now, you might be tempted to say, oh yeah, that's 0 comma 0, but there is no point there. The reason that there's an open circle is to show that there's nothing there. In fact, the only point on this graph that has an x value of 0 is this one down here. This is the point 0, negative 2. Trying one more, g of 1 equals, well, if I do g of 1, we go to the x-axis at 1, and we ask ourselves, is there a value on the graph that will have an x value of 1? And I think there is. That is this point right here. When x is 1, what is the y? Well, the y is also 1. And so we have the point 1 comma 1. All right. Last part is we did need to write the equation or the equations for the branches. I say equations because it looks to me like there are 2 branches to this piecewise function. I'm actually going to start with this wall right here. This wall occurs at x equals 0. One function is going to be to the left of 0, and one function is going to be to the right. So let's start with that. We have one function that is to the left of 0, and one function that's to the right. Notice that the function to the left of 0 also has a closed circle here, and so that tells us to the left of 0 is also going to be equal. Now, how do we actually write the equations? Well, I think slope-intercept form is a great way to go. Slope-intercept form is nice as long as you have a nice y-intercept. So I'll do this first one in red, just outlining it. Do we have a nice y-intercept? We do. The y-intercept is negative 2. So I know this equation will end with negative 2. To use slope-intercept form, we also need to include the slope that's multiplying by x. So what is our slope here? It looks like it goes down 1 to the right 1, doesn't it? So I think negative 1 over 1 is totally fine, and that would be okay for your final answer. You could also just say that this is negative 1, or if you really wanted to be simplified, you could just say negative x. All those mean the same thing. So the first branch of this piecewise function happens for x is less than or equal to 0, and it's the equation negative x minus 2. We have one more, and I'll do this one in green over here. Okay. This one has a y-intercept of 0. Okay, so we could do plus 0 right here. And then what's the slope? Well, it looks like it goes up 1 over 1, doesn't it? So that's going to be 1 over 1x. Now, maybe the more common way to write this is you leave off the 1 over 1, you just put x because we always know there's a 1 in front of it, and then you'd also leave off the 0 because we know that you can always write in a plus 0, but you don't have to. Now that you get the idea, we should probably try these last couple out. So, next one, and again this one should probably say h of x. Let's rock and roll. What does h of 0 equal? Well, this is 0 comma something. Here's 0 on the x. What is the y value that brings you up to the equation? Oh, it's right here. This is the point 0 comma 3. So when x is 0, y is 3. So h of 0 is 3. What about h of 3? H of 3, well, that's 3 comma something. Here's 3 on the x-axis. Is it going to be 3, negative 3, or 1? And the answer is, of course, 1 because we have that shaded in circle. So 3 comma 1. H of 3 is 1. Last but not least, we have h of 4. Here's 4 on the x-axis. Where does that go? Well, no y value brings it onto the graph here. But, oh, there's a point on our graph, and that point is 4 comma something. 4 comma what? Well, that looks to me to be 4 comma 3. So when 4 is substituted into my h of x equation, we should get an answer of 3. Let's write these equations as well. H of x equals, well, we can kind of split this into a few different pieces, can't we? We have what happens at 3, we have what happens greater than 3, and we have what happens for less than 3. Okay? So notice that one function is going to be hanging out with the less than 3 part. One function, this green dot down here, happens exactly at 3. And my last line happens just to the right of 3, or greater than 3. Filling these pieces in, okay, we have the one in left, and I'll do that one in red. Does it have a nice y-intercept? Why, yes it does. The y-intercept is positive 3. Write a little bit smaller here. There we go. I have to fit 3 equations. And then what's the slope? Down to the right one. So we could say negative 2 over 1x plus 3, or more commonly just negative 2x plus 3. All right, let's see what happens at 3. Well, at 3, we just have a single point. At 3, we have an output of 1. There's just a single point there, and so we can say when you substitute in 3, the answer is simply 1. Our final equation is this horizontal line, making sure we remember how to do horizontal lines. If you expand this out, you'll notice it crosses the y-axis at 3. So this horizontal line occurs when y equals just plain old 3. All right, let's look at our third question. Finally, my f of x matches. We have 3 pieces here. Okay, our first wall occurs at negative 1, and our second wall occurs at 3. We have all the points, or the line that is to the left of negative 1, the line that's to the right of 3, and we have the line that's between negative 1 and 3. And that one's a little harder, so if you ever struggle to write that, you can always look back on previous problems. X has to be between negative 1 and 3. We always use less thans. Negative 1 is less than x is less than 3, and we should be good. All right, let's do our points first. What is f of negative 1? Well, here's negative 1. We don't go up there. That's an open circle. We go down there. There we go. That's f of negative 1. This is the point negative 1, negative 1. And so now we know the value of f of negative 1. What about f of 1? Well, f of 1 is, well, here's 1 as the input. The output brings us up to the graph, and so this is the point 1, comma 2. And last but not least, what is f of 3? F of 3, we'll do this one in blue. Okay, let's see, f of 3, here's 3. What brings us up to the graph? Oh, not that high, right? That wouldn't be good. We need to stop at the closed circle. There is f of 3, which is 2. That's the point 3, comma 2. All right, we have 3 equations to write. Let's do those restrictions first. The one that I'm going to do in yellow over here is good for x less than negative 1. However, we should also notice that there's a closed circle here, so it's actually less than or equal to -1. The function in the middle is between -1 and 3, so -1 is less than x, which is less than 3. Is it closed on any of those? Yeah, I think it is. There's a closed circle at 3, but not at -1, so an equals on 3. Last but not least, we have this guy over here. Starts at 3, and it's only to the right or greater than 3. And you might have noticed that there was no equal sign on 3. The equal sign already got used up here. Let's write those three equations. The first one I'll do is in yellow. It's this guy over here. If we wanted to use slope-intercept form, we'd have to think, does this have a nice y-intercept? Well, the first thing that hopefully springs to mind is you can't even see the y-intercept, right? The y-intercept occurs on the y-axis, and it doesn't even get over there. Now, you could be sneaky, and you could use the slope to go down 1 to the right 2, down 1 to the right 2, and you can kind of draw it out a little more. But you might realize that it still doesn't have a nice y-intercept. Now, you might say, ooh, I bet that's -1.5, and you'd be right in this case. But why go that hard? Why go that far? I tried to say hard and far at the same time. Well, all we need to really do is just use HK form here, I think. Our slope goes down 1 to the right 2. So I know it's going to be down 1 to the right 2, and then HK form. We just need a point. I already have a point on here. -1, -1. Do the opposite of h and keep k the same. And therefore, this yellow function is going to match what's on the screen. Okay. Then we can go through and move on to our next one. Hopefully this one's a little bit easier. This next one is just the horizontal line at 2. I'll do this one in green, and I think that one is just 2. Any input you get, the output must be 2. Last but not least, done in blue, we have this guy over here. And again, you could trace this up until you find the y-intercept, but it sounds pretty awful. Let's just pick a point on here. How about this one? This is the point 4, 3. My slope is down 1 to the right 1. And we're just going to go ahead and go through and say we know the slope is down 1 to the right 1. HK form, we used the point +4, -3. So opposite of h, and sorry, that should be +3. Okay, +3. It is totally okay to leave off the -1/1 and just leave it as like this. X - 4 + 3 with the negative out front. Either one is totally fine. All right, as we finish off this video, we have 2 problems remaining. Our first one has to do with Jody's babysitting. Okay, Jody will babysit a maximum of 7 hours. I guess we should probably record my times maybe in orange. For the first 3 hours, Jody charges her customers a rate of $5 per hour. If she babysits for more than 3 hours, then she charges her customers a total of $30. Let's get that one in there too. Regardless of how long she sits for. I mean, she only sits a maximum of 7 hours. I was like, can we hire her for like 2 days and like take a vacation? No, I guess not. Write a piecewise function called C of t that has 2 branches to represent the total amount Jody charges after t hours. Well, let's start with the restrictions first, this piece over here. Okay, I see a couple restrictions. First, Jody babysits a maximum of 7 hours. For the first 3 hours, so from 0 to 3 hours, she charges a specific amount. So I would say, looks like t is our input here. I would say that for this first one, t has to be between 0 and 3. Okay, and then our second equation, Jody's going to only babysit from 3 up to 7 hours. T has to be between 3 and 7. All right. Now, it says up to 3 hours for the first 3 hours, so I think 3 is included in this one, and 7 is included here. Maybe you could also include 0. Right? We don't want to include 3 here because it says for more than 3, not equal to 3. All right, let's get down to the writing equations. Actually, the second equation is easier because it says if she babysits for more than 3 hours, then Jody just charges her customers $30. So that's pretty nice. If you use a time between 3 and 7, you know the answer is just 30. However, for the first 3 hours, she charges her customers a rate of $5 per hour. And it might help you to think about this to say, well, if she babysat for 2 hours, how much would you pay her? Well, $5 per hour times 2 hours I think would be 10. It seems like whatever your time is, you have to multiply it by 5. And that is how we come up with our second equation, which is just 5 times t. If we wanted to find each value and explain what they meant, then to do c of 2, we have to ask ourselves, which equation do we use for c of 2? Well, our input, our time of 2, is in between 0 to 3, so we use the top branch, 5 times 2, which is 10. What does that mean? Well, it means Jody makes $10 for babysitting the input 2 hours. Full disclosure, you should pay your babysitters more than that. Like we pay ours at least like $15 an hour right now. So, but either way, let's move on. C of 5. Well, C of 5, 5 is between 3 and 7, and so that is just $30. It's just with 3. Okay, and same idea. Jody, so she makes $30 for 5 hours. Nice. Okay, I think we get the general idea here. Now, there is a last page here, but I imagine I probably won't have enough time with my students, and you probably won't with yours. If you want to work through the last page on the packet, it's a good one. It talks about speeding tickets in Michigan. It's a real-world problem, too. I looked up different speeding laws and found that this is how it works in Michigan. So this is all about a piecewise function, and you'll actually find that piecewise functions tend to be probably the most real-world, realistic application of mathematics you'll come across, right? If you want to talk about teacher salaries, those are piecewise functions. Depending on the amount of years you worked, you make different amounts of money. If you want to talk about temperature, piecewise function, right? It's all over the place, and it just goes to show that most things in the real world aren't going to be modeled by a single equation. You need many different equations. So thanks for sticking around for piecewise functions. We, next class, are going to start to bridge the gap between piecewise functions and something you've learned before in middle school, absolute value.